Since remote times, man has used natural substances to keep their food or heal their illnesses. Today, besides studying the chemical reactions that occur in our bodies, chemists are working in various fields directly related to health. Many medical diagnoses are based on tests performed through simple chemical reactions. For example, the determination of blood glucose, pregnancy tests, among other tests. One of the great advances that have marked the 20th century, and obviously continue to shape the 21st century, is the development of medicine. The contribution of the chemical industry has been fundamental to many fields, but especially in the field of health. According to the purpose they serve, different kinds of medicines are distinguished. Antibiotics inhibit or kill bacteria and other microorganisms. Antipyretics reduce fever. Analgesics relieve pain. And anti-inflammatory reduces inflammation. Some medicines are substances of simple composition, for example, hydrogen peroxide, iodine, sodium bicarbonate, aluminum hydroxide, silver nitrate, potassium chlorate, among others. All medicines contain its active ingredient, which is the substance that produces the desired effect, and medicines also contain excipients. These are used to achieve the desired pharmaceutical form, such as capsules, tablets, and solutions. Also, facilitate the preparation, storage, and administration of medicines. Generally, the excipients are considered inert substances which have no pharmacological effect. Still, there are other excipients that may have an effect on certain conditions, in allergies, intolerances, skin reactions, among others. Chemistry facilitates hospital care. One of the main applications are antiseptics and disinfectants that allow safe operations. Anesthetics are other applications of chemistry in hospitals that have become essential in many medical interventions. Furthermore, the discovery of new chemical molecules increases the possibility of transplant tissues and organs and new gene therapies. Orthopedic prostheses, heart valves, artificial organs, or the surgical thread are made of high-tech chemicals. Syringes, blood bags, and serums, the plaster, the alcohol, hydrogen peroxide, and anesthesia products are common but not less important in our lives.
First of all, let's get things clear. While physics studies the mechanics of the universe and biology describes how life functions and interacts with itself, chemistry lies between them. So, let's talk about a little thing called global warming and the big concentrations of carbon dioxide in our atmosphere that are causing it. And I will start with something called the carbon cycle. The carbon cycle is the thing that makes Earth airy, unique among planets we now understand. Earth's atmosphere is made of gases, like ammonia, methane, nitrogen, and of course carbon dioxide. Many of these gases, including the carbon dioxide, are what we now call the greenhouse gases because, as we know, they absorb the heat that increases the average temperature on Earth. Plants go along with the photosynthesis process that, as we know, is the process through which plants use carbon dioxide, water, and light to create their own food and release oxygen into the air. Plants start to create life by absorbing great amounts of carbon dioxide and transforming them into oxygen to create a whole new atmosphere. These changes not only help to open up Earth's atmosphere, allowing huge amounts of heat to radiate back into space, they also created the huge reservoir of organic forms of carbon. So, using these organic forms of carbon is the greatest way to trap more heat in our atmosphere, and that's why when we talk about global warming, we talk about carbon, but not only carbon, carbon footprint, carbon credits, or carbon loading. So let's wrap things up by going not to the first, the second, the third, fourth, or fifth, but the sixth element in the periodic table of elements, which is carbon.
Since carbon is the stuff of life, one of the best ways of understanding the carbon cycle is just a whole bunch of things living and dying, and in the process, swapping carbon. Here's the 30-second version. Plants use the carbon in atmospheric CO2 to make sugars and other carbohydrates to grow and reproduce. Lots of those plants end up being eaten by other organisms, supplying them with the building blocks for other biological molecules and fuel. After being metabolized, the carbon returns to the environment in one of several different ways, ending up in the air, water, or the earth itself. From that point, it's released naturally or is extracted by humans, in either case returning carbon dioxide to the atmosphere, and it starts all over again. So let's talk about those green plants and what exactly it is that they do. Photosynthesis is an extremely complex process, and it can happen in a couple of different ways, depending on the organism. But the main point is to take in carbon dioxide from the environment and use a process called carbon fixation to convert it to organic compounds such as sugars. It's called fixation because it takes carbon in the form of a gas, carbon dioxide, and solidifies it into solid carbon compounds. The general reaction looks like this. Note that CH2O isn't actually a thing. It's a reduced formula that stands for a simple carbohydrate, a compound that's composed of carbon and hydrogen and oxygen in a ratio of 1 to 2 to 1. In real life, there are all kinds of carbohydrates, and they're usually a lot larger, but chemists use this streamlined version to illustrate the basic reaction. And the reaction is basically the same with any hydrocarbon, but you've probably seen it written most often with glucose. In this form, we say that 6 moles of carbon dioxide plus 6 moles of water plus some light energy yields a mole of glucose plus 6 moles of oxygen. Either way, you might have noticed something important. This is a redox reaction. Carbon is reduced, going from an oxidation number of +4 to 0, and oxygen goes from -2 to 0, meaning that oxygen is oxidized. It can happen. And the carbohydrates produced by these carbon fixation reactions are the most sought after currency among Earth's living things, because organisms can use them in 2 different ways, as building material and as fuel. Some carbohydrates go through additional reactions to become even more complex, like starches, fats, proteins, nucleic acids, and all the other stuff that makes up living things. Meanwhile, other carbohydrates, the ones that are used to produce energy, go through a process called cellular respiration. Like carbon fixation, respiration is an extremely complex cluster bomb of reactions, so we typically condense it too down to a fairly simple reaction. The overall reaction for respiration is essentially the reverse of carbon fixation. A carbohydrate and some oxygen react to produce carbon dioxide, water, and energy. Again, this is most commonly written with glucose, so we'll do that here too. And like carbon fixation, it's also a redox reaction. In this case, the oxygen is reduced from an oxidation number of 0 to -2, and the carbon is oxidized from 0 to +4. That's right, the cells of living things reoxidize the reduced carbon and re-reduce the oxidized oxygen to produce all the energy that keeps living things alive. But despite the fact that these 2 reactions look like exact opposites of each other even down to the changes in their oxidation numbers, it's important to remember that they're just summaries. The overall processes actually include lots of steps that are completely different from each other. Now, after organisms metabolize carbohydrates, the carbon can be released back into the world in several ways. For one thing, lots of carbon dioxide is released as a direct product of cellular respiration. For you and me, that happens mostly when we exhale, and that carbon dioxide can be recycled immediately by photosynthesizers. For organisms that live in water, the carbon that they release largely ends up dissolved in that water, and oceans and other surface water can also dissolve carbon dioxide directly from the air. No matter how it gets there, carbon dioxide reacts with water to form carbonic acid, a weak acid that dissociates into hydrogen and bicarbonate ions. The hydrogen ions can react with various rocks and other substances in fairly typical neutralization reactions. This results in weathering, which besides melting the faces off of statues, produces stuff that forms clays. But the carbonate ions have a whole bunch of functions, especially in marine animals, which use them to build their shells and skeletons in the form of calcium carbonate. The carbon remains trapped there until those animals die and their structures break down, which happens on huge, very slow geologic timescales. And if the conditions are just right, like in the super high pressures and temperatures in the Earth's crust, large deposits of calcium carbonate can eventually form rocks like limestone. And before you start thinking that rock equals boring, you should know that about 80% of all the carbon on the planet is locked up this way, as inorganic carbonates in the Earth's crust and mantle, or lithosphere. Most of the remaining 20% is spread throughout the lithosphere too, as organic carbon from buried organic matter. So, those pools of carbon that everyone's so obsessed with, those fossil fuels that we use to power all the things, they account for only 0.006% of all the carbon on Earth. Those carbon deposits got there from the dead bodies of other organisms like plants that managed not to be eaten or have their carbon released some other way. Hence the name fossil fuels, dead things that you know today as coal, petroleum, and natural gas. The general chemical reaction for combustion of those fuels is just a hydrocarbon reacting with molecular oxygen to form carbon dioxide and water vapor. For example, each mole of methane, the simplest hydrocarbon, reacts to form 1 mole of carbon dioxide. And of course, this too is a redox reaction, where carbon is oxidized all the way from -4 to +4, and oxygen is reduced from 0 to -2. Combustion is an extremely common reaction type. The only change that occurs from one example to the next is the hydrocarbon. And obviously, as larger, more complex hydrocarbons are used, the CO2 production per mole of fuel increases. What about gasoline, for example? Combustion of octane, a main ingredient in gasoline, produces 8 moles of carbon dioxide for every 1 mole of fuel used. A mole of octane is only about 0.15 liters, or 0.041 gallons, but those 8 moles of CO2 take up nearly 180 liters of space at standard pressure and temperature. This carbon dioxide is released back into the atmosphere, where it re-enters the carbon cycle. The problem with all this is that the environment can only reabsorb about 40% of the 30 million tons, or gigatons, that humans produce annually. So we have a surplus of about 18 gigatons of CO2 every single year, and that number goes up every single year. The excess remains in the atmosphere, trapping the sun's heat, causing temperatures to rise. And yes, there are other greenhouse gases too, methane, ozone, even water vapor, to name a few, but none of these are increasing in abundance at nearly the rate that carbon dioxide is. The good news is that now you understand the problem better than you did 10 minutes ago, and understanding a bad situation is the first step to making it better. That goes for all situations, really, not just chemistry ones, so continue to pay attention to what's happening in the world around you, keep learning science, and never stop caring. And thank you for the difference you made by watching this episode of Crash Course Chemistry, and this entire Crash Course Chemistry course, which I hope you watched. In this episode, you learn that the carbon cycle includes carbon fixation, both cellular and macroscopic respiration in living things, and deposition in limestone and fossil fuels, and that many of the chemical reactions involved in the carbon cycle are redox reactions. And finally, you learn from a chemistry perspective exactly why excessive burning of fossil fuels harms the environment. And I'd especially like to thank all of our subbable subscribers, without whom we would literally not be able to do this. Would you like a personalized, signed, giant Crash Course periodic table, or even to see yourself animated in one of our future episodes? To find out about these and other perks, go to subbable.com. And thanks too to our skilled writer Edie Gonzalez, script editor Blake DiPastino, and our chemistry consultant Dr. Heiko Langner. This episode was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Michael Aranda, who is also our sound designer, and our graphics team is Thought Cafe.
When we chew, aromas are released that activate our sense of smell by way of a special channel that connects the roof of the throat to the nose. If this channel is blocked, such as when our noses are stuffed up by a cold or flu, odors cannot reach sensory cells in the nose that are stimulated by smell, so we don't enjoy foods the same way. Without smell, foods tend to taste bland and have no flavor. A huge amount of chemical compounds contribute to the flavor of food. Chocolate, for instance, is a mixture of some 300 flavor compounds, and coffee beans contain more than 800 chemicals. Identifying these chemicals can help create a variety of artificial flavors that are used in nearly every food product out there, including potato chips, ice cream, chewing gum, and soft drinks. Chemists create artificial flavors from chemical compounds present in plants and animals. They use them in their natural state, or they process them to make new flavors. What's interesting is that we don't need all the flavor compounds in a given food to recreate its flavor. For instance, an orange contains 250 flavor chemicals, which all combine to create an orange flavor. But artificially flavored Tang, a powdered drink mix, has only 6 aromatic chemicals in its makeup, but it has a familiar orange-like taste. So we can get pretty close to proper orange flavors from just a few of its flavor chemicals. Artificial flavors get their characteristic odor from various compounds, especially esters, which are chemical compounds formed by the chemical reaction of an alcohol with a carboxylic acid. An alcohol is an organic compound with the general formula ROH, in which the R is a hydrocarbon group and the OH is a hydroxyl group. A carboxylic acid is a compound with the general formula RCOOH. For example, the formation of ethyl butanoate, one of the compounds that gives pineapple its flavor, is produced through the reaction of butanoic acid with ethanol. But wait a second, isn't ethanol the type of alcohol found in alcoholic beverages? That's true, but when it combines with the acid, it loses the characteristics of drinking alcohol. Likewise, acetic acid is the main component in vinegar, yet when it reacts with an alcohol, the flavor changes dramatically. When two compounds react to form a new compound, the properties of the new compound are not a simple combination of those original ones. They are completely different. If you use different alcohols and different acids, you obtain different flavors. You can compare that to combining two colors of paint. When you combine red and yellow, you get orange. Similarly, when you combine pentanol with acetic acid, you get pentyl acetate, an ester that smells a lot like a banana. Flavor chemists combine many chemicals to achieve a desired scent. Day after day, they test different combinations before settling on the one that will achieve the desired result. But don't expect to get a tour of a flavor and fragrance factory anytime soon. Those flavor formulas are carefully guarded industry secrets. At major food companies, you have to work as an apprentice chemist for 7 years before even getting a peek at the flavor formulas behind the world's most popular foods.
Science has impacted and taken part in all aspects of human life. Everything around us is made part of the chemistry. The objects we use daily are products of the chemistry, from our food up to the clothes we wear every day. This science has partly benefited humans, but like everything in life, the human race has not properly taken advantage of the benefits of chemistry, and goes to the extremes of self-destruct the planet on which they live. Chemistry is a branch of science that is basic and indispensable for the development of humanity. but has been misguided its use and its application, and instead of improving the world, we are getting worse. We have to find solutions to the pollution problems that currently exist in order to preserve our race. I think that chemistry has taken a big step in the evolution of the world, but not everything that has been invented based on chemistry has been helpful, but quite the opposite. Destroys the world and causes conflicts between countries. I have highlighted much this part of chemistry because it was for me one of the most important parts, besides being the section that corresponded me. Chemistry, as the other science, looked for ways to improve aspects of life. This was regardless of the damage it would cause to other things. The environment is one of the most affected as it was in a balance until our intervention. Therefore, it has become a necessity not only to stop the damage, but find ways to reverse it. The chemistry is a science. The fact to classify it between good or bad is something wrong. That is, it all depends from what point you look at it. The man decides how to use chemistry and in which area use it. Chemistry has contributed many important scientific advances. It is also fundamental to the development of life as we know it. But we must also consider that man has been given it not as beneficial uses, and how its misuse could result into damage of the planet to the extinction of a race. We believe that people need to make conscience about long-term problems that can lead to the misuse of chemistry, and damage that can be avoided by using the benefits of chemistry in a moderate and responsible way.